In this video, we're going to discuss the base number system, three of the most popular base number systems, and how to convert between the three. To introduce the topic, we're going to talk about a base that everyone's familiar with, base 10. Base 10 is the system we use every day, and how it works is any base 10 number can be represented by the equation shown here, where 10 to the power of some number p multiplied by some number n is added to another one of these expressions. P is determined by the place or position the number is holding. The rightmost number is represented by p equals 0, and since we're dealing with base 10, there are 10 possibilities for n, 0 through 9, and that's the number we read. Now you may already know how base 10 works, but to make it more clear, I'm going to use this example number 456. The first position in a base 10 number is called the ones place, and since the ones place here is the first position in number, this tells us the p number for our first addend is going to be 0. In our example here, the ones place holds the number 6, which is our n number. So what we get for our first addend of the equation is 10 to the 0 power, or just 1, multiplied by 6, which is simply 6. If we keep working our way to the left, we hit the next place, the tens place. As we keep moving throughout the number, the value of p will increase by 1. So the p value for the next addend is 1, and the n value is 5, given to us by the number. So the next addend of the equation would be 10 to the 1 times 5, which equals 50. And then we hit our last step, which is the hundreds place, and our p value is now 2, and our n value is 4. So our final addend for the equation is 10 squared times 4, which equals 400. Using our equation, we can now see how 456 gets its value. It's 400 plus 50 plus 6, and this equation can be stretched out to infinity to hold any number. Elementary schools commonly use these blocks shown here to teach young students how base 10 works, and provides an excellent visualization to our equation from before. If we use these blocks to represent our example of 456, then we'd have 6 of the 1 blocks, 5 of the 10 blocks, and 4 of the 100 blocks. And if we put them all together, we have 456 individual 1 blocks. So now that we understand base 10 thoroughly, we can use it as a reference to understand other bases. We're going to introduce 2 more bases, base 2 and base 16, and use the prior equation to convert these bases back into base 10. First, we're going to discuss base 2, otherwise known as binary. Now you've probably seen these numbers before. They're called binary and are the famous ones and zeros that computer science has been built on. Binary is the language that computers use to comprehend information using electric signals. While binary may seem confusing, foreign, and hard to read initially, this isn't really the case. We can use our equation from before to convert base 2 numbers into base 10. As you can see, because we're now dealing with base 2, 2 is raised to the power of p instead of 10, and n can only be 2 digits, 0 or 1, instead of 0 through 9. We approach the example number 1101 the same as 456. So let's start at the first position to the right, and we start at p equals 0 just like before, and our n number is 1. So our first addend to the equation is 2 to the power of 0 times 1, which is 1. For our next place to the left, p is now equal to 1 and our n number is 0. So our next addend is 2 to the power of 1 times 0, which is 0. For the next place to the left, p is now equal to 2 and our n value is 1. So our next addend is 2 to the 2 power times 1, which is 4. And for our final place, p is now equal to 3, and our n value is again 1. So our next addend is 2 to the power 3 times 1, which is 8. Our whole equation comes out to 1 plus 0 plus 4 plus 8, which equals 13. So as we can see, converting a base 2 number to a base 10 isn't as difficult as one may think, and we could just slightly alter the equation from before and use that. So now we're going to show how we convert from base 10 to base 2, because we already did base 2 to base 10. So we're going to use our same example of 13 since we already know the answer. Now what you want to do, anytime you convert from base 10 to another base, you start by dividing by the desired base. So we're going to do 13 divided by 2. We know this is 6, remainder 1. Now the remainder is really important, and this is what we really want to keep track of. So we're going to write that over here to the side. Now we have 6 divided by 2. And that's 3, remainder 0. So we're going to write down our 0. Now we have 3 divided by 2, which is 1, remainder 1. So now we have 1. And then we have 1 divided by 2. Now 2 doesn't go in, there's 1. So this is 0, and then remainder 1, because there's 1 difference between these. So our last digit's 1. And that was our example from before. So that is how you convert from base 10 to base 2. You do this little division algorithm here. Now the final base we're going to discuss is base 16, or more commonly known as hexadecimal. The hexadecimal system is very common on the internet, and in the computer science world. One common use of hex numbers is holding color codes, which are numerical representations of visible spectrum colors. Now, as we've seen already, we can use our equation to calculate hexadecimal into base 10, just like with base 2. But now that we're dealing with base 16, 16 will be raised to the p-value, while n could be any of 16 values. And since we can't use base 10 numbers, 10 through 15, we use alphabetical letters A, B, C, D, E, and F for these numbers, where A equals 10, B equals 11, and so on to F equals 15. So n could be any number 0 through 9 plus these letters. So let's use this example, A5E, as an example. Like we've done before, with our first place, P is going to be equal to 0, and our n value is now E, which represents 14. So the first addend of our equation is 16 to the 0 times 14, which is 14. So for the next place, P is equal to 1, like we've been doing, and our n value is 5. So our next addend is 16 to the 1 times 5, which is 80. And now for our final place, P is equal to 2, and our n value is A, which represents 10. So our next addend is 16 squared times 10, which equals 2,560. So our full total equation is 14 plus 80 plus 2,560. So our hex number A5E equals 2,654 in base 10. So now we're going to go over converting base 10 to base 16. And we're going to use our same example from before, again, because we know the answer. So we start the same way. 16 is our desired base, so that's what we're going to be dividing by. So this is going to come out to 165, remainder 14, right? Did it in the calculator. So then we write down E here, because 14 is represented by E in hex. So now we go 165 divided by 16. For this, we're going to have 10, remainder 5. So 5 is our next number. Now we're going to do 10 divided by 16. And now 16 doesn't go in here, so it's 0. So 0 times 16 has a remainder of 10. It wouldn't be a remainder of 6, because you work from 0 up. So this is remainder 10. And 10 is represented by A in hex, so it's A. And that was our example from before. So that's how you convert from base 10 to base 16. The next conversion we will discuss is base 2 to base 16. So doing this conversion isn't quite complicated and doesn't involve any kind of algorithm or formula. Let's use this number as an example. The size of the number may seem overwhelming, but we can break it down into 4 sections of 4 bits as shown. And a bit is just simply one binary digit. So by doing this, we can treat each section of bits as an individual conversion by starting at the rightmost group of 4. So 0010 has a 1 in the 2's place, so this is 2. 0001 only has a 1 in the 1's place, so this is 1. And we already converted 1101 before and found it to be 13. However, it's base 16 now, so this will be D. 1001 has a 1 in the 1's place and a 1 in the 8's place, so this value is 9. We can simply write all our conversions down in the order we were given, and now we're done. Our base 16 conversion is 9D12. Now the last conversion we're going to discuss is from base 16 to base 2. Now this is really similar to the last example, and we're going to use 4A1B as our example number. We can start on either end of the number since the conversions are all independent, so we'll start at the right. And we're going to convert each hex digit into a 4-bit group. So B represents 11, so we can either use division or intellect to convert 11 to binary. We need 8 plus 2 plus 1, so this is 1011. Next we have 1, which is simply 0001. Next we have A, which represents 10, so we need a 1 in the 8's place and the 2's place, so this is 1010. And finally we have 4, which is simply 0100. And now we've completed the conversion from base 16 to base 2. And you're able to do them all independently, and if you added up all the binary numbers, it would still be equivalent to the huge hexadecimal number we started with, even though we took it piece by piece, which is really kind of cool. That brings us to the end of the video. I hope this helped you understand base systems, and importantly, base 2, base 16, base 10, and how to convert between the three.